Hey everyone, and welcome back to AI Pulse Trends. We talk a lot on this channel about the incredible pace of progress in artificial intelligence. But what if I told you that the very foundation upon which AI runs, classical computing, might soon be complemented and, in some cases, transformed by something even more powerful, something that taps into the bizarre rules of the universe itself? Today, we're diving headfirst into one of the most exciting and potentially revolutionary intersections of technology, quantum AI. We're going to explore how the mind-bending power of quantum mechanics is merging with the intelligence of AI to unlock possibilities we could only dream of just a few years ago. We'll break down what quantum AI actually is, how it works, the astonishing problems it could solve, and the significant hurdles we still need to overcome. If you're fascinated by the future of computing and intelligence, you're in the right place. Make sure you're subscribed and have hit that notification bell so you don't miss our deep dives into the future of tech, classical versus quantum computing basics. All right, let's set the stage. For decades, computing has been built on the classical bit. Think of it like a light switch. It's either on, 1, or off, 0. Every piece of data, every instruction, every calculation, no matter how complex, is ultimately broken down into sequences of these definite zeros and ones. This classical approach has given us everything from the computers you're watching on to the most powerful supercomputers on Earth, and it's powered the first wave of AI. But there are certain types of problems that even the most powerful classical supercomputers struggle with. These are problems where the number of possibilities grows exponentially, trying to simulate the behavior of complex molecules or finding the absolute best solution among an astronomical number of choices. These can take thousands, millions, or even billions of years for a classical computer. Classical computing hits fundamental limits when dealing with problems involving vast combinatorial spaces or simulating quantum mechanical systems accurately. The power of qubits, superposition, and entanglement. Enter the quantum computer. Instead of classical bits, quantum computers use qubits. And this is where things get weird and powerful. Unlike a classical bit which must be 0 or 1, a qubit can be 0, 1, or a combination of both simultaneously through a phenomenon called superposition. Imagine a spinning coin before it lands. It's neither heads nor tails definitively until it stops. A qubit in superposition is like that spinning coin, representing a probability distribution of states. It's not a fuzzy 0 or 1, but rather exists in a state that is a linear combination of both, described by probability amplitudes. But the real magic happens when you have multiple qubits. They can become entangled. Entanglement is a bizarre connection where the state of one qubit is instantly linked to the state of another, no matter how far apart they are. Measuring the state of one entangled qubit instantly tells you something about the state of the other. This creates complex, interconnected quantum states that can represent vastly more information than an equal number of classical bits. Two classical bits can be in one of 4 states, 0, 0, 0, 1, 10, 11. With an entangled qubit, you can represent a superposition of up to 2 n states simultaneously. This exponential scaling of the state space is the source of quantum computing's potential power. This ability to exist in and manipulate multiple states simultaneously, and the correlations provided by entanglement, is what gives quantum computers their potential power. Instead of trying possibilities one by one, a quantum computer can, in theory, explore a vast landscape of possibilities all at once through clever quantum algorithms. This is the source of quantum advantage, the point where a quantum computer can perform a task demonstrably faster than the best classical computer. It's a fundamentally different way of processing information. Quick recap. Now let's talk about AI. Artificial intelligence, in its modern form, is fundamentally about creating systems that can learn from data, identify patterns, make decisions, and solve problems. Machine learning and deep learning have revolutionized tasks like image recognition, natural language processing, and predictive analytics. AI algorithms crunch through enormous data sets on classical computers, identifying correlations and building models. They excel at recognizing patterns in large data sets, but still face computational limits when dealing with extremely complex, high-dimensional or quantum mechanical data. The convergence, quantum AI explained. So where do these two revolutionary fields meet? This is where quantum AI comes in. Quantum AI isn't just about running existing AI algorithms faster on a quantum computer. It's about developing entirely new AI algorithms and approaches that leverage the unique capabilities of quantum mechanics, superposition, entanglement, and potentially quantum tunneling to solve problems that are intractable for classical AI. It's about creating a new class of AI, one that can operate in a quantum realm and potentially outperform its classical counterparts on specific hard problems. Think about training a complex machine learning model. This often involves navigating a vast, bumpy landscape of possible parameters to find the optimal set. Classical algorithms can get stuck in local minima. Quantum algorithms, particularly those based on quantum annealing or quantum approximate optimization, might be better at exploring this landscape and finding the global optimum more efficiently by leveraging quantum effects. This could lead to faster and more accurate model training for certain types of AI tasks. Quantum machine learning, QML, and quantum neural networks, QNNs, quantum machine learning, QML, is a rapidly developing subfield at the heart of quantum AI. Researchers are exploring how to adapt classical ML techniques or invent new ones specifically for quantum hardware. This includes several approaches: quantum-enhanced classical ML, using quantum computers for specific computationally intensive parts of a classical machine learning workflow. For example, speeding up linear algebra operations central to many algorithms like support vector machines or principal component analysis. Quantum algorithms like HHL can solve linear systems exponentially faster under certain conditions, potentially accelerating parts of classical ML. Other algorithms can potentially speed up matrix operations or sampling. Quantum algorithms for data analysis. Developing purely quantum algorithms designed for tasks like clustering, classification, and dimensionality reduction that can either process data encoded in quantum states or leverage quantum speedups on classical data. Examples include quantum k-means or quantum PCA. These algorithms aim to find patterns and structure in data more efficiently by operating on superimposed and entangled states. Quantum neural networks, QNNs, aiming to build neural network-like structures directly on quantum hardware. QNNs leverage the interconnectedness of qubits to potentially model complex correlations in data hard for classical NNs to capture. These are still in their infancy, often using parametrized quantum circuits trained similarly to classical NNs but operating on quantum data or quantum representations of classical data. The hope is that quantum correlations could lead to new forms of learning or allow learning from less data for certain problems. Quantum optimization for AI, using quantum optimization algorithms like quantum annealing or QOLA to find optimal solutions for AI-related problems such as training model parameters, selecting features, or optimizing network structure. Optimization is a core component of many AI tasks, and quantum approaches could provide speed-ups or find better solutions for complex landscapes. Unlocking unprecedented possibilities. Applications overview. The potential applications of quantum AI are truly staggering and span across numerous fields. By combining the pattern recognition capabilities of AI with the computational power of quantum mechanics, we can start to tackle problems that were previously considered impossible. Let's explore some of the most promising ones in more detail. Application 1: Drug discovery and materials science. This is perhaps one of the most impactful applications. Designing new drugs and novel materials requires understanding the intricate interactions between atoms and molecules. These interactions are governed by the laws of quantum mechanics. Simulating the behavior of complex molecules from first principles is incredibly computationally intensive classically, because the number of interactions grows exponentially with molecule size. Even with supercomputers, simulating molecules with more than a few dozen atoms accurately is a significant challenge. Understanding these molecular interactions is crucial for designing new drugs, predicting material properties, and designing new catalysts. Quantum computers are inherently suited for simulating quantum systems like molecules because their qubits can map onto the system being studied. Quantum algorithms like VQE and quantum phase estimation are being developed to calculate molecular energies or simulate dynamics. These calculations are fundamental. Quantum algorithms could allow us to accurately model properties currently impossible or prohibitively expensive to simulate classically, dramatically accelerating the discovery and design process. Imagine being able to virtually screen millions of potential drug candidates much faster and more accurately, or designing a new battery material or a more effective catalyst from scratch. Quantum AI, by combining AI's pattern recognition with quantum simulation power, could revolutionize the pharmaceutical, chemical, and materials industries, leading to faster innovation and solutions to global challenges. QML could potentially identify subtle patterns in simulation data that guide the search for new materials or compounds. Application 2. Finance and optimization. The financial world is another area ripe for quantum AI disruption, particularly in complex optimization and simulation. Portfolio optimization, choosing the best mix of assets to maximize returns while minimizing risk, becomes exponentially harder with more assets and constraints. Finding the absolute optimal portfolio is a highly complex combinatorial optimization problem. Similarly, risk analysis often requires simulating a vast number of market scenarios. Fraud detection involves analyzing massive datasets for subtle patterns. Algorithmic trading relies on identifying complex patterns and optimizing execution. Quantum optimization algorithms such as quantum annealing or QoA are showing promise in finding better solutions or finding them faster than classical heuristics for certain financial optimization problems, including portfolio optimization, risk management, and clearing processes. These quantum algorithms can explore the vast landscape of possible solutions in a fundamentally different way, potentially avoiding local optima. QML could also play a significant role. By analyzing complex financial data with quantum-enhanced techniques, QML algorithms might build more accurate models for predicting market movements, identifying subtle patterns indicative of fraud, or optimizing trading strategies by finding complex correlations missed by classical methods. The ability of QML to handle high-dimensional data and model complex relationships could lead to more sophisticated financial models. Application 3. Cryptography, threat, and opportunity. Cryptography is where the potential impact of quantum computing is perhaps most stark and urgent, presenting both a significant threat and a unique opportunity. The threat comes from Shor's algorithm. This quantum algorithm demonstrated that a sufficiently powerful, fault-tolerant quantum computer could efficiently factor large numbers. The security of widely used encryption algorithms, most notably RSA, relies on the fact that factoring large numbers is computationally intractable for classical computers. Shor's algorithm makes this task feasible, meaning a powerful quantum computer could break much of the encryption used today. While a large-scale quantum computer capable of running Shor's algorithm reliably is likely still a decade or more away, the threat requires action now. Data encrypted today could be stored and decrypted later. This is why there is intense research into post-quantum cryptography, new mathematical algorithms designed to be resistant to attacks from both classical and future quantum computers. AI could potentially assist in analyzing the strength of these new algorithms. On the flip side, quantum mechanics also offers quantum cryptography, specifically quantum key distribution, QKD. QKD allows two parties to share a cryptographic key whose security is guaranteed by physics. Any attempt to intercept alerts the parties. While not a replacement for all encryption, QKD provides a theoretically unbreakable method for establishing secure keys. Other key applications. Beyond the areas we've deep dived into, quantum AI holds promise across many other domains. Optimization for logistics and supply chains. Complex logistical problems like routing trucks or optimizing schedules involve finding the best solution among an enormous number of possibilities. Quantum optimization algorithms are being explored to find more efficient routes and schedules. QML could analyze patterns in supply chain data to predict disruptions or optimize inventory. Advanced scientific research. Quantum computers are ideal for simulating other quantum systems. This is crucial for chemistry, materials science, and fundamental physics, allowing scientists to model particle interactions or simulate quantum materials beyond classical reach. QML could help analyze vast data from particle accelerators or telescopes, identifying patterns of new physics. Weather and climate modeling. Simulating complex global weather patterns and climate change is incredibly computationally intensive. Quantum optimization or QML techniques could potentially improve specific aspects of these models, such as atmospheric process simulations or data assimilation. Artificial creativity and generative models, more speculative, but quantum computers' ability to explore vast state spaces could potentially be leveraged in generative AI models to create novel art, music, or designs by exploring combinatorial possibilities differently than classical methods. Major challenges in quantum AI. It sounds like a technological utopia, doesn't it? But we need to be realistic. Quantum AI is still very young, and there are significant challenges before these possibilities become widespread realities. Hardware limitations, scalability and error rates. Building quantum computers is incredibly difficult. Qubits are extremely fragile and susceptible to decoherence, losing their quantum state due to environmental interaction, heat, noise. Decoherence leads to errors. Current quantum computers are NISQ, noisy intermediate-scale quantum devices with limited qubits and high error rates. Noise limits the complexity of calculations. To run powerful algorithms or achieve significant advantage, we need fault-tolerant quantum computers with millions of reliable qubits protected by sophisticated quantum error correction. Developing effective error correction and implementing it physically is a major challenge, requiring many physical qubits per logical qubit. Scaling up while maintaining quality is a monumental task. Software and algorithmic development. We lack a mature library of quantum algorithms. Developing algorithms for current or near-term hardware that provide a practical advantage is hard. Translating classical problems into a quantum framework is non-trivial. We also need better quantum programming languages, compilers, and tools to make quantum computers more accessible. The quantum software ecosystem is rapidly evolving but still nascent. Data handling, input, output, and encoding. Getting classical data into a quantum computer efficiently and in a way that leverages quantum properties is a challenge, the quantum data loading problem. Extracting results back into a classical format is also difficult. Developing efficient methods to encode classical data into quantum states and perform measurements without destroying quantum information is crucial for QML. Talent gap. Quantum AI requires expertise at the intersection of quantum physics, computer science, mathematics, and domain knowledge. Professionals with deep understanding of both quantum mechanics and AI are rare. We need to train a new generation of the workforce to develop, operate, and utilize quantum AI effectively. Cost and accessibility. Current quantum hardware is extremely expensive to build and operate, requiring specialized infrastructure. Access is mostly limited via cloud platforms. Widespread, affordable access is needed for broader research and commercialization. The economic model is still evolving. Ethical considerations. As with any powerful technology, QAI raises ethical questions. Breaking encryption needs proactive mitigation, post-quantum cryptography. We also need to consider societal impact, including potential job displacement and ensuring equitable access to the benefits and preventing misuse. Responsible development and governance are crucial, the road ahead and future trends. Despite these challenges, progress is being made at an incredible pace. Major tech companies, startups, and academic institutions are investing heavily. We are seeing rapid advancements in qubit quality and quantity. We are currently in the NISQ era, focused on finding practical applications for smaller, noisy quantum computers and developing hybrid classical quantum algorithms. In these approaches, a classical computer handles the overall workflow, while the quantum computer acts as a co-processor for quantum advantageous subroutines. The roadmap towards large-scale, fault-tolerant quantum computing involves significant engineering breakthroughs in error correction and hardware. This is a long-term goal, likely still a decade or more away for general-purpose fault-tolerant machines. But even before fault tolerance, NISQ computers are expected to offer demonstrable advantages for specific problems in optimization, simulation, and early QML. The future of quantum AI is not about replacing classical computers. Classical computers are excellent at many things and will remain the backbone. Instead, quantum AI is about complementing classical AI, tackling problems currently out of reach, and opening new frontiers in science, engineering, and AI. It's a journey of collaboration between the two computational paradigms. Unlocking the next frontier in computing and intelligence is the driving force. From designing catalysts for energy solutions to creating personalized medicine to building AI that understands the world in new ways, quantum AI holds the key to solving humanity's most complex challenges, pushing the boundaries of what's computationally possible. So, there you have it. Quantum AI is the fascinating convergence of two of the 21st century's most transformative technologies. We've journeyed from the difference between classical bits and quantum qubits, explored how superposition and entanglement power new computation, seen how these capabilities enhance and redefine AI through QML and QNNs. We've looked at the incredible potential applications revolutionizing drug discovery and materials, optimizing finance and logistics, and fundamentally changing cryptography. And we've also faced the reality of the significant challenges: the fragility of quantum hardware, complexity of developing quantum algorithms, handling data, the talent gap, and the need for ethical considerations. Quantum AI isn't science fiction. It's a vibrant, rapidly evolving field. While widespread fault-tolerant quantum computing is still some years away, the progress being made today is laying the groundwork for a future where the possibilities become tangible realities. It's a future where AI isn't just smart, but quantum smart, capable of tackling problems on a scale we can barely imagine, pushing the boundaries of what's possible. What are your thoughts on quantum AI? Which application do you find most exciting? Which challenge do you think is the biggest hurdle? Let us know in the comments section below. We love hearing from you and discussing these cutting-edge topics. If you found this deep dive fascinating, please give this video a thumbs up. It really helps the channel. And if you haven't already, hit that subscribe button and ring the notification bell so you don't miss our future explorations into the cutting edge of artificial intelligence and technology trends. Check out these other videos on our channel where we explore other groundbreaking areas of AI. Thank you so much for watching, and join us next time on AI Pulse Trends.